All right, let's look at those trig limit identities that we're going to memorize and see how we can apply them to solve for other limits. So let's remember these three identities while we scroll down and try 6. If we can get something in that form, then we can always replace it with a 1 or a 0. So for number 6, I have the limit as theta goes to 0 of sine 2 theta over theta. It almost looks like this first identity, except something's not right. This theta has to match this. And here it doesn't match. This is 2 theta and I have theta. If I can get them to match, even if they're not both theta, as long as whatever they are matches, if I get 2 theta in both spots, then I'll be able to apply this theorem. So what I'm going to do is multiply. I need to get a 2 into the denominator. So I'm going to multiply the denominator by 2. But I don't want to change the value, so whatever I do in the bottom, I got to do in the top, so I get 2 over 2. But I do have a theorem that says I can take the constant out. I can change the order of this multiplication a little bit. So I'll bring this 2 into here, and this 2 I'll bring out in front of the limit. So I get 2 theta in the denominator and sine of 2 theta in the numerator, and I still have this times 2 from here. But that 2 is a constant, and the limit law says I can bring a constant out in front, which gives me 2 times the limit as theta goes to 0 of sine of 2 theta over 2 theta. Now this limit looks a lot like this one. The only difference is that I have 2 pi 2 theta instead of 1 theta. So if I had my limit as 2 theta goes to 0, that would make it match. And as 0 theta goes to 0, 2 theta goes to 0 as well. So we can still apply this theorem, this identity here, and say that this limit is 1. So then we have 2 times 1, so this limit equals 2. In number 7, we can apply a similar technique. This time we have a 5 theta in the numerator, and we have a 6 theta. So I need to multiply both sides of the fractions by the same thing so I don't change the value. But the other thing I'm missing in 7 is I don't have any theta by itself. So what I'm going to do is think of the numerator and denominator separately, and I want to get that theta in the denominator, like I had in number 6, in each of those parts. So I'm going to multiply both the numerator and the denominator by 1 over theta. So when I multiply those together, I get something in the numerator and in the denominator that looks like what I had in 6. So in the numerator, I now have sine of 5 theta all over theta. And in the denominator, I have sine of 6 theta all over theta. If I just had one of these, then I would do exactly what I did here in number 6. So I'm going to do that within the pieces of the fraction. So in the numerator, I'm just going to treat that one and multiply it by 5 over 5, just like I did for number 6. In the denominator, I multiply by 6 over 6. So now I'll have my sine 5 theta over 5 theta is here, and that 5 that's left over will come out in front. Same with the 6, so sine 6 theta over 6 theta is here, and the 6 is left over to come out in front. So I'm going to rewrite that a little bit. So theta goes to 0. So now I'm going to move this 5 with the theta. So I have sine 5 theta over 5 theta. And I still have that leftover 5. And then I have sine 6 theta times 6 theta times the leftover 6. The leftover 5 over 6 will come out to the front. So I get 5 over 6 times the limit as theta goes to 0 of sine 5 theta over 5 theta all over, not all over, sorry, just this piece over 6 theta over 6 theta. Now with the quotient rule of limits, remember this is not a derivative, so we don't have to do the quotient rule where we do low-d high or anything like that. We just do the quotient rule of limits says that if I have the limit of a quotient, that's equal to the quotient of the limits. So I have 5, 6, and then I can take it piece by piece. So the limit of this piece is 1, and the limit of this piece is 1. So then I just get 5 over 6 times 1, which equals 5, 6. Going on to number 8. Here we have the limit as theta goes to 0 of sine of theta squared over theta. Notice the square is on the theta, so it really means this, which is not the same as this. So this is the theta is being squared and the sine is being taking the theta squared. So that means I have this this extra theta that I have to match, right? So look, to make it look like this law, I want this piece to match this piece. So with that problem, I have a theta squared in the numerator, so I need to get a theta squared in the denominator. So just like we did with the constants, and we multiplied it by the missing piece, we're going to do the same thing here. So I'll multiply it by theta over theta. So I get the theta squared that I want in the denominator, but I still have that extra theta in the numerator. So that gives me the limit as theta goes to 0. This piece is 1, and then that leaves me the, so that's sine theta squared over theta squared. And I'm just going to split it up because the limit, remember the limit of a product is equal to the product of the limits. So I can split it up like this. And then I could use direct substitution for the second one. This one, we know the limit of that is 1 because that's our identity that we're going to memorize. So that equals 1 times the limit of as theta goes to 0 is just 0. So I get 0 for 8. Now in 9, it looks very similar to 8, but that square being over here with the sign means that I actually have sine of theta squared. So it looks like that. In this one, I already can see this part will go to 1, and then I can take the sine of theta separately. So I'll separate my product again. So I have the limit as theta goes to 0 of sine of theta times sine of theta over theta, and I can separate the limit by product. So that gives me the limit of the first piece is sine of 0, which is 0. And the limit of the second piece we know is 1. So 0 times 1 is 0. Number 10 is a little different. So 1 over theta is a funny one because you can't ever plug in a 0 for that denominator. And that function behaves like a sine function, but as it gets closer and closer to 0, it just keeps going up and down and up and down, but it can never cross the 0. So it gets incredibly, infinitely closer and closer together as it gets to 0, but never crosses. So, and same from the left, if I take the right-handed limit, then it approaches 0 in this way, but again, it can never actually cross 0, so it just keeps oscillating, trying to get closer and closer to 0, but never getting there. So since it's oscillating between -1 and +1, it doesn't actually approach any one number. So this one does not exist. The right-hand limit and the left-hand limit are both oscillating forever, infinitely infinitely towards 0. So that's an interesting function. I just remember if you have sine over 1 over the input, then that function does not exist. That limit does not exist. So there's our practice problems with a couple techniques and how to use those limits to prove other limits.